Okay, great. So it looks like everything's working. So yes, the next speaker is Steve Flammia, who's kind of local here, and he'll be telling us about randomized benchmarking with confidence.
Thank you. And I'd like to thank my opening act, Dave Wineland. Just kidding. It's kind of intimidating going after Dave, but hopefully you guys are still interested. I guess none of you ran off to the coffee break, so I'll try to say something interesting. This is joint work that I did with Joel Wallman, which you can find here on this with this archive preprint. So the sort of motivating thing that motivates this whole field, the central result in quantum computing, is the fault-tolerant threshold theorem. And you know, this is not a talk about fault tolerance, so I'm going to give a very rough sketch of what this theorem says. It basically just says if you want to do a quantum computation of indefinite length, then you can do that with low overhead, provided that you have a gate error rate, which is less than some number epsilon, and the correlations between your gates are sufficiently weak. Now, you need a little bit more than that, of course. You need some parallelism. You need fresh ancillas and things like this, but these are the two things that I want to focus on in this talk as requirements for fault tolerance. And so, you know, the way I sort of blithely state it here, it sounds easy. So if you're one of the founders of quantum computing and the ideas behind quantum fault tolerance, then you might wonder, you know, where's my quantum computer? And you know, we just heard, so what's the answer to this question? Is it that Dave Wineland isn't working hard enough? Well, I don't think so. We just heard this great talk about all the wonderful work that's going on at NIST and in 30 some odd other groups, and that's just doing ion traps. So I don't think it's for a lack of effort on the part of the experimentalists. It's just really hard. So even when you have a mustache this cool or this cool, it's a very challenging problem. And you know, as I said, ignoring some of the other issues about parallelism and things like this, the bottom line is epsilon, no matter what scheme you consider, is pretty small. When you start putting in realistic architectures and things like this, it's on the order of 10 to the minus 3 for your 2-qubit gates. And you know, these are pretty generous assumptions when you get numbers like this. There are schemes where it's higher, on the order of more than 1%, but these things tend to have astronomical overheads, or even bigger numbers like economical overheads. So when you get down to lower numbers, even the lower numbers, the overheads are still quite demanding. So despite the best efforts of very good experimentalists, you know, we don't have fault-tolerant quantum computation. So then the question arises, is our computers working? Some of you get the Bush reference, others may not. I was going to put an NSA joke in, but I figured they've heard them all already. So the overhead requirements prohibit a direct demonstration, even if you're just under the threshold, right? I mean, what's the obvious way to demonstrate that you have a working quantum computer? You just sit there and do arbitrarily long quantum computations, factor giant integers, things like this, right? But we can't do that when we're hovering around the threshold because we just don't have enough qubits to do, let's say, a concatenated encoding scheme or any of the other schemes and actually demonstrate that we have very long-lived logical qubits. So this overhead precludes that very obvious option. And also, so everyone in the audience of a theoretical bent is going to say, well, you know, you have some error rate that's order epsilon. All you have to do is just measure that thing 1 over epsilon squared times. You just sample it, and then you're done, and that's polynomial, so there's no problem. The problem is that if epsilon is 10 to the minus 3, and remember that was generous, then what you're essentially asking is for the poor experimentalist in the lab to do about on the order of 1 million experiments just to get this one number. And you know, these things are really hard. So complexity here is a practical bottleneck for assessing these quantum devices at the level of the constants here, right? I mean, let alone the scaling. We're still after better scaling on these sorts of protocols. But even with our best protocols, we really do care about the constant when it comes time to making a connection with the experiments. I mean, everyone knows this in certain contexts. So what do we really want when we're trying to assess some kind of quantum device? We want to evaluate our progress towards the ultimate goal of a fault-tolerant quantum computation. So experimentalists, and just as importantly, funding agents, they want standardized numbers that are comparable across radically different platforms. So they want to be able to compare, who was just mentioned, a superconducting architecture was mentioned. They want to compare superconductors with ion traps with any of the number of other architectures out there, even though this is definitely apples and oranges, but they want to be able to do it anyway. So we need to be able to derive sort of summary statistics that tell us about the quality of our gates. Ideally, these things should be operational. They should tell us, ideally, they should just be what the threshold is for that system within the context of some particular architecture. But that sort of number is a bit nebulous because it's a bit of a moving target. As theorists develop better fault-tolerant threshold schemes, that number sort of fluctuates. So maybe it's better to use certain proxies that still have an operational meaning, things like the trace distance for states, which is the worst case measure of distinguishing between two states, or the diamond distance between two quantum channels, which has a similar interpretation, but for quantum gates, or the gate fidelity, which is a notion of average case error rates. So the complexity of obtaining a useful estimate of these proxy quantities should not be prohibitive on few qubit systems. So up to, I don't know, let's say a dozen qubits, but the more the better. So the more scalable, the better. So traditionally, there's been a solution, although there has been a lot of work transcending the original paradigm of state and process tomography. But originally, people used state and process tomography, and it worked great. And the reason it worked great was because the gates weren't very good. And so once you start getting more and more accurate gates, you start to find the following phenomenon. This is a graph that I took from a paper by Merkel. So they have some notion of noise power in their particular system, and this green bar is the noise power regime that's relevant for their particular experiments, or at least the ones they were doing at that time. And as you turn that noise power down, each of these curves here is a depolarizing channel. This is some noise model for their noisy qubit. So this is 10% depolarizing noise, 1%, and so on. As you turn down the noise power, you can do as many experiments as you like, right? So you're gathering more and more statistics, turning down this noise power. You eventually hit a noise floor below which you cannot get a more accurate estimate in state tomography. So state tomography in this context does not converge to an arbitrarily accurate estimate, okay? Why is this? Well, to understand why this happens, imagine you're sitting at your desk, you're doing a quantum computation. It's a very small desk. This person's gonna have back problems in a few years. So you're doing your quantum computation, you do your very delicate gate with a 10 to the minus 4 average error rate or something, and then you go to measure it to recover some statistics, and pow, you're hit with spam. And that means state preparation and measurement errors. So these are the errors that are intrinsic to, roughly speaking, quantum computations break into three parts. There's the preparation, there's the application of the gate, and then there's the measurement. And when you do quantum state tomography, you're conflating the noise associated to those three very distinct processes. Now, I just want to mention in passing that there has been some work recently on spam-resistant tomographic methods. There's this idea of gate set tomography and this idea of using something called interleaved randomized benchmarking to get tomographic information about gates that may not be as sensitive to this idea. But I'm not going to talk about that. Go find, I don't know, I think Robin is at least in the audience. I'm not sure if Marcus da Silva or Shelby Kimmel are in the audience. Anyway, there are people here that you can talk to about those things if you're interested. So randomized benchmarking, okay, this is another solution which avoids the idea of trying to get complete information about your gates. So I think it's Mark Twain who said the key to success is two things: ignorance and confidence. And so benchmarking, this talk is about confidence intervals for randomized benchmarking. So that's the confidence bit. And the ignorance bit is we're going to ignore all of the extraneous information that we get when we try to do tomography. we're going to throw away all that extra information, and we're going to ignore the spam, and we're just going to focus on the average gate error rate. And here's the way that we're going to do it. And that'll lead to success in the sense of Twain. So here's how we're going to do it. So in this diagram, time moves from right to left, because that's the natural way that operators act. So here's the protocol. This was first written down by Emerson, and then I believe independently by Knill, and they did the first experiment in 2007, actually, published in 2008. I have a bunch of Clifford gates that I choose at random. So I choose a sequence of M independent random Clifford gates. Now I'm going to have to compile these Clifford gates in general into elementary gates that I can actually perform in the lab. So if this is like a 5-qubit system that I have here, I need to break those 5-qubit random Clifford operations into 2-qubit, 1 and 2-qubit Clifford gates. But the elementary, the atoms that I'm interested at the level of the analysis are the Clifford gates themselves, not these 2-qubit elementary gates. So I break up, I pick M random Clifford gates, and then I pick one extra gate such that the product of all of these is the identity. Okay, so this sequence is a sequence of M plus 1 gates, which is M-wise independent. Okay, and then I'm going to prepare some initial state, which I'm trying to prepare, let's say, the 0 state in the computational basis, and then I'm going to measure in the computational basis. But you know, maybe these things are a little bit noisy. So in general, I'll label them with rho and with E, some POVM effect E. And then I'm going to apply, I'm just going to measure, and I'm going to do this many times, and I'm going to get an estimate of the probability of getting some outcome E given this label for the sequence and the initial state rho. This is some fidelity, right? And I'm going to repeat this many times to get an estimate of this. And I'm going to do this for many different values of M. And at each value of M, I'm going to repeat this for many different sequences. Okay? And each individual sequence, I'm also going to repeat that sequence many times to get statistics. Okay, so there's a whole lot of averaging going on. What happens when you do this particular procedure? So this I took from the first benchmarking experiment from the NIST group. You get a bunch of data points, and as the sequence lengths increase, you know, we're not doing any error correction or anything. We're just doing random sequences of gates. So you expect that this fidelity will decay, and it's going to spread out too, because the different sequences, some of the sequences will have a kind of spin echo type effect and will maybe correct themselves a little bit. And others might do the opposite. They might sort of enhance some error, right? You might have error enhancement in some of the sequences. So you expect that this thing will decay and spread out, okay? And so you look at that and you say, well, I'm going to fit a line to that, and that's going to be my proxy measure for the decay rate of these curves. What does this decay rate mean? So we can relate this back to one of those averaged quantities that I mentioned before. In fact, it's related to the average fidelity, which the average fidelity is, I was trying to do the identity gate, right? I prepare perfectly, I prepare the state psi, and I try to do the identity gate, but I have a slightly noisy gate, lambda, which instead acts on the state. And so I just do this integral over all input pure states. This is the average fidelity, okay? This analysis is called the zeroth order analysis, and I've taken this diagram from Grenade, Ferry, and Corey, a nice paper published last year, which I have a little bit more to say about later. Oh, and I just realized they used the wrong way of time. I should have reversed that. So we prepare some initial state, and we're going to break up each one of these gray globs here is a real Clifford gate sitting in your actual experiment. Okay, and I can always break that Clifford gate into an ideal Clifford gate, U1, followed by the action of the noise. Okay, I can always do such a decomposition. So I do that for each of these Clifford gates, and then I do some noisy measurement. And what I'm interested in is the expected value of this, right? I'm trying to derive that this is equal to some function of the average gate fidelity. So I can split this U2. I can factorize this into U1 dagger times, V1 dagger times V2, and I can call this V1. right? So now I'm conjugating this by the same unitary. I'm conjugating this. I do the same for U3, etc. And now I'm conjugating the noise by the same unitary operation at every time step, okay? And I can pull this expectation value through. So in the 0th order approximation, we ignore the fact that there are m+1 fold dependencies, and I just approximate this sequence as being completely independent. And I just pull this expectation value through, and I do the average over the full unitary group. And I get just the product of these averaged noise channels at every time step, plus some noise on the input and some noise on the output, which I'll take into account separately. Okay, so what this sequence is doing, what all of this averaging is doing, is it allows me to treat this as the power, the n-fold power of the channel, right? So if I think of this channel as a linear map, which I apply n times as a linear operator, this is the n-fold power of this channel. So what is the answer for this averaged channel? So if I were to choose these things, not necessarily from the Clifford group, but from Haar random, like an average from the full unitary group, I would get this integral. But if instead I can choose them from any 2 design, so a unitary 2 design is something that reproduces exactly the second moments of the Haar measure. So I can replace this integral with this discrete average over the Clifford group. You could use other unitary 2 designs as well, and some people have looked at that. And then I can use Schur's lemma to just write the answer, right? So it's going to be some linear combination of the identity channel and the maximally, the identity channel and completely depolarizing. So it's a depolarizing, it is a depolarizing channel with some error rate f, and you can compute this error rate exactly. It's given by this quantity here in terms of the average gate fidelity. Okay, so this is the 0th order model for benchmarking, and we've eliminated all of the extraneous information, and so now what we can do is we can when you push the analysis a little bit further, you find that at every sequence length m, you can fit at 0th order to the following model: a plus b f to the m, where f was this quantity here, which depends on the average fidelity, which is our figure of merit. So this is not actually a linear model. I mean, it's very close to linear. So these quantities a and b, I didn't write the expressions for them, but they don't depend at all on the error rates. They only depend on the SPAM, the state preparation and measurement errors. This gives me a way to so the slope is the only thing. I mean, I'm ignoring the fact that this is not a linear model, so there's a small caveat there. But roughly speaking, the slope of this line tells you exactly about the error rate, and the offset tells you something about your state preparation and measurement errors. So by doing this, we've managed to decouple these 2 noise sources, which was the bugbear for tomography. Yeah? M is the sequence length, right? So we did a sequence of M Clifford gates. Any other questions? Okay. So a natural question to ask is, how can we do an optimal experimental design given a little bit of prior knowledge? Okay. So experimentalists always have a little bit of prior knowledge. They've done a few experiments. They know something about their system. How can we leverage this into choosing the optimal choice of M, the optimal number of random sequences to choose, and things like this, so that the poor grad student sitting there tuning the lasers doesn't have to spend eternity trying to get an accurate answer? In order to answer this question, we need to know how the variance changes as a function of M and what I call the error rate R, which is just 1 minus this figure of merit. So this is kind of the natural quantity if we want to do an expansion in terms of small r, because f is, as we heard, very close to 1. It's so this average error rate in experiments for single qubits goes anywhere between 10 to the minus 2 all the way down to, there was a recent experiment that claimed 10 to the minus 6. I don't know if I believe them, but it can get very small. and M is on the order of anywhere between 100 and 1,000. So the product M times R, which is what we're going to expand in, is a very small number. So in order to answer this question about optimal experiment design, we need to know how the variance changes as a function of M and R. So if you do a naive analysis of this problem, you run into a bound on the variance which is constant and is bounded only by the spam, right? So the spam rears its ugly head again, and these two parameters, A and B in our fit, that control the spam, these things are constants. They don't depend on the error rate, as I mentioned. And the best upper bound that you can get using a sort of naive analysis is upper bounded by some constant. When you do this analysis, it's a bit suggestive that this constant shouldn't be there and that the real answer should be linear in M times R, okay? If you do this analysis and then you push it through to the end, you wind up making recommendations to experimentalists that each one of those data points, each one of these things should be averaged 10 to the 5 times. Thanks. And then you get on the order of millions of experiments that they would have to do to get any sort of confidence in their answer. Fortunately, the experimentalists just ignored those recommendations and they didn't spend an eternity in the lab. So what we did is we've refined this analysis. So our contribution is to reduce this calculation of the variance from a constant down to something order M times R, right? So remember, M is order in present experiments 100 to 1,000. R is anywhere from 10 to the minus 2 or 3 all the way down to 10 to the minus 6. So this is much, much smaller than the constants that you get from the naive analysis. We have a general bound for D-level systems, which has dimension dependence, which we don't think should be there. But more interesting is the special case of qubits, where almost all benchmarking experiments take place. And we have a much stronger bound than linear in MR. We have something proportional to M squared R squared. Moreover, if you're confident that your noise is dominated by noise which is diagonal in the Pauli basis, such as depolarizing or dephasing noise, you can improve this to MR squared, this upper bound of the variance. We also prove in our paper some robustness guarantees that if this varies weakly with time or there's slight deviations from Markovianity, we can still recover results of similar flavor. So those are just numbers. What does this actually mean? Our bounds are really, really tight. So here what we did is we sampled a bunch of channels. There's a characterization of qubit channels given in this paper by Ruskay, Zarek, and Werner. You can sample from the set of channels that have error rates on the order of, I forget what the particular error rate was for this, for these numerics, and then you plug in our bound and you find that it essentially exactly tracks those states. So this bound is a very good guide for how to choose optimal values when you're doing your experiment. In my last minute or two, I just want to mention some of the methods. I definitely don't have time to get into it, and you probably don't care that much anyway. If you did, you've probably already read the paper. But the analysis is kind of delicate. We write down an expression for the channel, and we have to do the tensor power of the noise channel averaged over this group G. This is the Clifford group. So this is the twofold tensor power of G raised to the nth power. So this is kind of a very nasty expression. And then we need to optimize over tensor product input states, positive states. If you do that more generally, you get terrible wrong answers. So it's kind of a hard analysis. Schur's lemma is not enough because it's not a strong enough group average. So you're left analyzing these non-normal matrices, and you have two different terms. So you wind up subtracting the nth power of this matrix from this matrix, and you require very delicate cancellations. And you have to analyze the sort of spectral gap of this tensor power, which has been averaged over a tensor product of group representations. So the analysis is basically bounding this non-unital contribution. We use some fancy inequalities, the von Neumann-Trace inequality, and a whole lot of hard work and sweat, most of which was done by Joel Wallman. In the last maybe minute, I just want to mention a little conjecture that we have, which is this idea of an n-contractive channel. So we are able to use this idea of an n-contractive channel to prove bounds on the asymptotic variance. We can show that when you do these benchmarking experiments, in fact, in the very far asymptotic regime, the variance decays exponentially to some constant, which is given only by the amount of non-unitality. And so so an n-contractive channel is a map from density operator from d-dimensional density operators to d-dimensional density operators, for which I take the n-fold tensor power and I average it over some group. And it's one where this average channel has at most one eigenvalue of modulus 1. So it's contractive as a map with just one unique fixed point. Okay. So we conjecture that all non-unitary channels are 2 contractive with respect to any unitary 2 design. We can prove this statement exactly for the special case of non-unitary unital channels. And we can also reduce it to this special case of an equivalence. Sorry, we can reduce it to an equivalence statement about strongly irreducible channels, which were described in this paper by Sands et al. So I encourage you to think about this, although be forewarned, I told Michael Wolff and David Perez-Garcia about it, and they said, this result is obviously true, but it might take many months to prove. So I thought, okay, I'm not going to work on that. But if one of you has an insight, then great, let me know. So just to wrap up, the main result is that we showed a rigorous bound on the randomized benchmarking variance, which is much smaller than the naive constant bounds, and greatly improves over these sort of outrageously large constants that people had previously shown. Some open questions: can we go beyond the zeroth order approximation? Can we remove that dimensional factor, which occupies the leading order term for when we go beyond qubits? Can we do something? So the main obstacle to doing this is the plethism of the Clifford group. So when we break up tensor products of irreps of the Clifford group, we take tensor powers of irreducible representations of the Clifford group, we break them back up into irreducible representations. If we had a general understanding of this, we might be able to make some progress on this problem. And I speculate that there's a closed form solution that's possible for qubits. So that would be quite interesting. And another open question is, can we improve our mustaches to be more like Peter or Dave and improve our science in that way? And that's all I have to say. Thank you.
Okay, thank you very much, Steve. So some questions. Yes, let's start there.
I was just wondering if your conjecture can be stated in terms of the multiplicity of trivial irreps in that representation of that group. So whatever G is, there's a tensor product representation, right? And that average will be, commutes with that representation. And I was wondering if this conjecture, which states that the eigenvalue 1 is at most, 1, can be stated as the multiplicity of the trivial irrep of that group.
I don't think so. I think you need to know the full set of irreps that pop out when you do the tensor power. It's not enough to just understand the multiplicity of the trivial irrep.
Okay. Yeah. Thanks.
But I haven't thought hard about it. I mean, it might be. I'd be surprised, but I haven't ruled that out or anything.
So also in your conjecture, this may be a stupid question, but why do you have to say for any unitary 2 design rather than just for the unitary group, since it's a second power thing?
Oh, yeah. I mean, yeah. We make the conjecture a little bit more general about n contractive channels, where n is like the number of powers that you have, and so I think that's just a caveat associated with that slightly more general statement.
Okay. Is there any other question at the moment? If not, actually, I'd just like to ask one question. So you said it's about the tightness of your result. Mm-hmm. So you sort of showed this graph that you sort of claim that it's very tight. But
yeah, that's numerics.
Yeah,
I don't have a lower bound.
Okay, you don't have any lower bound. No. Okay, so that was the question. Okay, thanks. Okay, so if there's no further questions, let's thank Steve again. Okay, and now we have a